Hi. Okay, today I want to show how to figure out the volume of a solid whose cross section is perpendicular to the x-axis. So let me go directly to a problem which is typically asked for the AP calculus AB. That is, the base of a solid is a region bounded by the x-axis, which is the y-axis. The x equals 1, sorry, x-axis where the y equals 0. So this is y equals 0 because x-axis. And from x equals 1 to x equals 6. And the graph is given by y equals x plus 1. Now, I took this as an easy one just for the easy calculation to understand. And the question asked is, what is the volume of solid having each cross section perpendicular to the base is a square? So the first question is a square, or it could be also a semicircle, or it could be also a right isosceles triangle. So let's stick to this one is square. So if you want to, you may be given the graph of this or may not be, but let's see how the graph looks like. So what I'm going to do is, let me graph this as quick as possible. So how does the graph look like for y equals x plus 1? I'll just try to draw it right here. Okay, let me draw it right here. So here is it. So it is given from 1 to 6. So I get 1, 2, 3, 4, 5, 6. And this side it is 1, 2, 3, 4, 5, 6, 7. So how does the graph look like? Y equals x plus 1, the slope is 1, crosses the y-intercept is 1, so regular slope-intercept form starts at 1, and then you go, the slope is itself is 1, so I go 1, 1, so that's, then again I go directly, if I put x equals 6, because we need to do from, okay, we need to know from x equals 1, when x is 1, the y is 2, that's the first point, and when x equals 6, 6 plus 1 is 7, so I got it right here. And I'm going to join this. Okay, so what we do is we have to build a solid whose cross section, and it is bounded by the x equals 1, these are the bounds, and the x-axis. So this is the x-axis. So we need to draw squares which are perpendicular to this area from this whole section area. So here I have to have solid whose cross sections are perpendicular to the x-axis. So how do I do this? So we can take a typical one of the base here. Let's see, if I take a base right here. So let me take this as the base. And I want to draw a square perpendicular. So this is your y equals fx. I will put it x plus 1. I want to draw a square, so how do I draw this? So what I'm going to do is, it becomes a little difficult here to draw like this. So still I'm trying. So each one is a square. So you get a one square here. So every perpendicular, I have another perpendicular here. This is a perpendicular. I will have another bigger one like this. Bigger square. So we are going to add all these areas of the squares which are perpendicular to the x-axis and add them up, and we try to figure out the volume. So the formula of volume is actually it's the Riemann sum, infinity integral. Let's see, I can write from this is 1 to 6. I can write a to b. It's a summation. Sorry. Summation of f of xi into, or each area we can write axi. So each cross section has an area times the width, and this I is 1 to n. So I can have a fixed number of cross sections, and I try to add all of these areas and add them up. So that becomes the volume of the solid. But that itself is the Riemann sum from A to B, area of So this is the area of one cross section. So that's the formula. So how do we, so how does this look like? This problem is easy, just put it, the area of a square we know is, area of a square is side square. So this is x plus 1, which is your fx. So the area becomes f of x, the whole square. So that's all you're going to plug in right here. And we can easily do this problem from 1 to 6. And 2x plus 1, the whole square, and dx. And then the rest you know how to do. So the point is, how do I show this? How does it make sense geometrically, a three-dimensional figure? Because this is two-dimensional figure and it becomes difficult to understand what's going on here. So what I try to do is, I try to make a 3D figure, three-dimensional figure, which shows how this each cross section is really perpendicular to the x-axis, and that is shown by, here it is. First, I'm going to show whatever I have drawn is something like this. So what I have here is the same line here. That's the line y equals x plus 1, and each cross section, what I did is I built a cross section which are all squares. You can see they are all squares. So this is how it is. Looks like they are all perpendicular to the x-axis. So these are some of those cross section of a solid, but we can make them, we can get millions of infinite many each cross sections, but I took some of them just to show how does it look like. So it is from x equals 1 until x equals 6, and then I add up the each volume of this ax, ax1, ax2, ax3, ax4, ax5, and each one has the width. So that's the Riemann sum right here, which I was talking about, and that's the integral that helps. So I really hope it helps. Now this is when it is the cross section. So hopefully you can see how it is. So this is each cross section of a solid is a square. I spend quite a lot of time in, my wife, my daughter helps me painting and just try to make sense out of it, because if you can understand this, then this becomes easier. What is a semicircle is, instead of this, the main focus is how does the 3D solid looks like and how each cross section looks like. So this is how it is. My next question is, of course, the rest is easy. You can easily find the answer for this, where you can just use the power rule and you can do that, or you can expand and whatever. What if the question is asked, if it is a semicircle? So what I do, I plug this out, okay? So instead of a square like this, instead of a square, I want to have a semicircle. So what I'll have to do is, I'll have to cut here, and let me try this with the helmet. Let me try. So, I hope it I did not get my, so what I'm going to do is, I'm going to cut this out like this. So you cut this way, so I'm going to cut into two parts. There you go. And then I have to have a semicircle. So what I'm going to do is, this one I'm going to draw a semicircle. So I'm going to go midway and draw semicircle this way. So that's it. And you need to cut this out, and we can do exactly the same what I did for this example. We can cut each of the cross section and make a so let me try this, one of this. So I should have a better, it's not a good one, but anyway, just wanted to show. So that's why I got one, and also I have another one. So here it is. So that's the semicircle, and the main focus is if you have a semicircle like this, then what is this? This is your fx height, but to figure out that ax, this ax we need to know. So how do we find that ax is? Let me write it here. So your ax is a semicircle, and the formula for semicircle is half of the area of the circle, and that is half of the area of circle is pi times a square of the radius. So what is the radius? So this is your fx. So this becomes your fx divided by. So this will be half of this. So this is your fx. So this will be the radius when I draw a semicircle this way. So what I have is, let me show. Here it is. So this is your fx over 2. So that's the radius of the, so here it is. So if then I can just put it over here. So it is the square of the radius. So I can write fx over 2 squared. You work this out, this will be 2. 2 times 2 is 4, pi by 4. So this is like a formula you can remember always. So it's basically it becomes like a pi over 4. Pi over 4. What did I miss? So this one will be 8 pi away. Sorry about it. That's how you get the semicircle, and whatever it is, in this case, we can put in the integral formula there, like integral of 1 to 6, and you just put in this area function, which is this pi, put it outside, and then the fx is already, you know it is, this is x plus 1, and you know what, the rest. Okay, so that was about if the question was asked if the cross section is a semicircle. What if the cross section is a right isosceles triangle? So that means each one, whatever this semicircle, we are going to draw like this. If this is the semicircle, this is the main. So this is the right triangle. You can have when in a semicircle, angle is always 90 no matter where is the vertex, but the one when it is exactly at the center here at this position, you will see when these two are equal, that's when the isosceles right triangles. I have to cut this out. So each cross section could be the right triangle. The area of a triangle is half base times height. So this is how each cross section will be, and we can always build a lot of right triangle which are perpendicular to the x-axis. So what's the area of this? So that area will be, we know, let's take a quick 45, 45, 90 right triangle. This is the A, this is the side, then this becomes root 2 over 2 times A, root 2 times over 2 times A, and the area of this will be half base times height, which is root 2 times over 2 times A, again half of root 2 over 2 times A. Root 2 and root 2 crosses out with one of the two, and what is left over is you get 1/8. So you get 1/8 of A square. So this is not really, it is the same thing you multiply. I'm just doing it a little fast because I have a class coming in just 2 minutes. I hope I finish this. So half, so this root 2 root will cancel with one of this, and this will give you 4th. And basically it's 1/4 of the area of if you had a whole circle square, the whole square. This one is Now, this is only the formula to have 1/4 of whatever if this side is. Knowing this, we can write 1/4 of a squared. So what I'm trying to do is the formula reduces to. So this was your fx. So this is your fx, and you get this one. So the formula that I showed earlier was area becomes one area will be 1/4 of the whole square. And this is like exactly like what you have if I had to do a square like this. The whole one was fx squared, and it is 1/4 of that because you have 4 of them. Look at this: 1, 2, 3, and 4. So we need only the one of this. So it is 1/4 of the square. So it is 1/4 of square. Only for the semicircle it becomes pi over 8. Here it is pi over 8 of square, or basically it is pi by 2 times the right triangle isosceles. So what I'm trying to say is, I hope the objective of today's this video was just to show the 3-dimensional figure of a solid. When you make a slices cross section, they are perpendicular to the x-axis, and you can use this Riemann sum of the areas into integration form and get the answer. I only hope I did my job. So Martin and Gavin, Ashton, just make sure you get that part right, because if you can understand this, then all problems will look safe. So just wanted to show you. Hope I did a good job. Okay. See you. I'll try to make more video on 3Ds like this if possible. Bye. Thank you.